So last lecture we saw Johnson-Linus-Strauss lemma. Essentially, one way to think about Johnson-Linus-Strauss lemma is that we needed to project endpoints, right? Maybe there were endpoints in d dimensions, in RD, right? And we needed to project endpoints in the dimensions, and we were asking ourselves, how many dimensions can we project to such that most distances between these points are kept? Or how many do we need, how many dimensions do we need to project to so that the norms of these points are kept, right? So distances between endpoints is a total of roughly n squared over 2 difference vectors. So keeping the norm of those or the distances of between these is the same. So we're going to talk about norms, and then if we need to keep the distances, we just have to take the difference set, right? And basically what we saw is if we had to project, right, in a way that the norm is kept or preserved up to 1 plus or minus epsilon, or the norm squared, then roughly we needed k dimensions, right? So this is just what we did, right? Where k was roughly something like 1 over epsilon squared log of the number of points. Right, so this is what Johnson and Strauss told us, right? So then we could take some f that goes from, say, n dimensions to just k dimensions if k is around this, and the norms of all the points would be roughly kept, right? So let's say n points, a set S of points. Right, so so here the size of S is n. Right, and if we needed to keep the distances between them, we would just take the difference set, right? So it would just be the square, but you know, the square inside the log would just make a factor of 2. Okay, so now the question that we'll be interested in understanding today is, what if we know more about S? Right, what if we know more? Okay, how well can we do if we know more about S? Can we actually improve over this? Right, because Johnson-Linus-Strauss was a statement about any set S of points, right? The only thing that mattered was its size. But what if we know more? In particular, we want to understand things like the set of all possible natural images, or the set of all possible brain scans from, say, an MRI or something of this type, right? Where it doesn't even make sense to talk about how many they are, but there's a lot of structure. So it turns out that the answer to this question will be given by Gordon's theorem. Right, Gordon's theorem will be very well suited to answer this question. So Gordon's theorem, essentially what it will say is that the important quantity is the Gaussian width. Okay, I go here, so important quantity is Gaussian width of S. Okay, so what is the Gaussian width? We're going to take our points to be in the sphere, just to make things easier. Because if we want to keep say the norms up to a multiplicative factor, then it doesn't matter what actually the norm is, right? We can renormalize everything. So we're going to assume, that our set S is inside the sphere of d to the minus 1 dimension. Right? This is sort of without loss of generality. Right? Because if there's a point we want to keep its norm, then it's enough to just project it to the sphere to have norm 1, right? Because what happens multiplicatively to its norm doesn't depend, right? If I shrink it or extend it, right? And so without loss of generality, we're going to have this, and the Gaussian width is going to be the following. So the Gaussian width of a set S is going to be the expected value, right, of the maximum over the vectors in the set, the set S, the inner product between a Gaussian random vector in d dimensions and X, right? Where this expectation is taken over this vector GD, and GD is just a vector in d dimensions, is just a standard Gaussian. Okay, so the rule of the game here is we take, right? we take the following random variable, we take a Gaussian vector, and then we try to find the maximum inner product we can do with it within a point in our set, and we take that value, right? So it's like, if you think of our set in sort of in the sphere in some form, right? Maybe there's the entire sphere and our set is just a bit here. We take some Gaussian vector, we're just looking at the point sort of that it's most in that direction, and we take the length of that, right? Essentially something of this type, right? Or you know, or the length of the projection. And then we look at this quantity, and this will be the quantity that will govern the answer to this question. And it turns out that in general we will recover Johnson-Lindner-Strauss lemma, but we're going to be able to say much more. So the Gaussian width will be a central quantity to measure the size of the set, in the sense of how many dimensions do I need to project it to in order for its norm, for the norm of the vectors in it to be kept up to some 1 plus or minus epsilon factor. So as maybe this is not surprising by now, but one quantity that'll be important is to, of course, understand the Gaussian width of the whole space, right, of the whole d dimensions. And so a quantity that will definitely be important and play a role is the Gaussian width of the whole sphere, right? How many dimensions we're going to need to project to, right? If we have the whole space, then of course we need to project to the dimensions, right? And so this quantity will play a role as sort of, you'll see in a bit how this will play a role in sort of a normalizing way. Okay, so what is this? But it's also a good way of getting some intuition of what this quantity actually is, right? To compute it for a set that we of course understand very well. Right, so what is this? So this is the expected value over, right, this Gaussian vector in the dimensions of the maximum of x in the entire sphere of GD transpose x, right? But of course, you know, if you're maximizing over the whole sphere the inner product, then of course this is just equal to the norm of GD, right? The best possible thing to do is to simply take the vector x to be the vector GD normalized, right? So this is simply the expected value of the norm of this vector, right? Which we know is around square root d. Okay, but we're going to define it to be AD. Right, this quantity will show up a lot, and this is in fact around square root d, right? I mean, the norm of a standard Gaussian in the dimension is around square root d, and so AD is in fact smaller or equal than square root d, and bigger or equal than the square root d with the factor that looks a lot like 1. Right, square root d over d plus 1. Okay, so it's essentially square root d, and this will be an important sort of normalizing factor. Okay, so AD is around square root d. Let's leave that on the board. Okay, and it's already hinting a bit that, you know, the number of dimensions I project to, I should need to project to the dimensions, and in fact, we will see via Gordon's theorem that the Gaussian width is measuring how many dimensions we need to project to in exactly this way, in the sense that the number of dimensions you need actually is the square of the Gaussian width. Okay, but let's see Gordon's theorem. Okay, so here the model is a little different than the model in Johnson-Lindner-Strauss, where we were taking projections. Here, instead of projections, we're going to take random Gaussian matrices, right? So instead, we're going to take a matrix G, right? This matrix is going to be R times D, right? So effectively, I mean, you can view it as a map that takes points from RD into points from RK, right? Before this was a random projection, now it will be a matrix with Gaussian entries, right? So G has Gaussian entries. It's IID and 0, 1 entries. Okay, so of course, you know, we need to normalize, right? So that even on average, the norms get kept. And so the matrix we're going to use, right? So projections, like the embedding, I mean, it's not really a projection, but the projections, right? Because this is not really a projection matrix, but it'll be very close to 1. But the projections will be done with the matrix 1 over k g. Right, this way at least, you know, at least the rows will have norm 1 with or an expectation, right? Because 1 over ak is exactly the expected value of a vector, a standard Gaussian right, the standard Gaussian in d dimensions. Okay, and so now, columns. This is AK, right? We want to normalize, we want the columns to have on average norm 1, right? So that when we take something with norm 1, it gets an expectation, something with norm 1 on the other side. One easy way to see this is, okay, G is of course rotation invariant because they're just Gaussians. If we see what happens with G and the vector E1, which has a 1 on the first entry and zeros everywhere else, right? This is just the first column of G, right? So this will basically be distributed according to a Gaussian in k dimensions, the standard Gaussian in k dimensions, right? And the L2 norm of this on average will be AK. So we divide by AK so that when I put a norm 1 vector on this side, on average it will have norm 1 on the other. So at least on average, it is keeping the norms of at least one vector, right? Of course, it's funneling the space, right? It's going to somewhere with a lot less dimension, so it can't keep the norm of all of the vectors, but hopefully we'll keep the norm of the vectors in S. Okay, so now we're ready for Gordon's theorem. Okay, so Gordon's theorem says the following. It says if I take a set S inside the sphere, closed, okay, this is just technical requirement. Okay, of course, remember, if you keep the norm of vectors in a set S, you keep the norm up to multiplicative constants, the same ones, of any vector that's a multiple of a vector in S, right? So really, you're not just doing a subset of the sphere, you're doing the whole cone, right? The cone is just a set where you get to multiply by positive numbers, just expand or shrink vectors, and this stays within this, right? So you should think that if I have like a circle and I'm taking this part, this is my set S, really my guarantee works for any of these vectors, right? That's why we call this a cone. Okay, and so this theorem, what it says is the following. It says that in expectation, okay, the maximum rests in the set S of, right? So we want to understand how this matrix acts on vectors in S. Okay, and we would like that, you know, the vectors will have norm 1 because X is in S. Okay, this is X, of course. So we'll have norm 1. So we want the norm after we hit it with the matrix to be as close as possible. And so the maximum will be bounded by 1 plus the Gaussian width of S over AK, while the minimum will be bounded by basically the same thing. Okay, so this is Gordon's theorem. Now, what does this say? Well, what this says immediately is that we have basically that the norms are very close to 1, right? Basically, we have that 1 over AK G preserves norm of points in S, provided that, right, AK is considerably bigger, let's say, I mean, right, depending how much we want to preserve, but we would like this to go to 0, is a lot bigger than the Gaussian width of the set S, right? Because AK is roughly square root K. Basically, this preserves as long as K is considerably bigger than the Gaussian width squared. right? So here we're immediately getting a theorem that says that now the amount of the amount of dimensions we need to project to, sure, these are not really projections, but they will behave essentially the same way, right? And we know exactly how the eigenvalues of this are not exactly one by looking at things like the Mashenko-Pasteur and so on, or the singular values, say, right? They'll be just the square root of the eigenvalues of the Gram matrix, which will be a Wishart matrix and will satisfy the Mashenko-Pasteur distribution, right? But we're seeing that the right sort of dimensionality of a set S is given essentially by the square of the Gaussian width, right? So now this allows us to do a lot of things, right? This will allow us to compute Gaussian widths of sets of interest, even if they're not sort of explicitly defined, like the set of all natural images and things of this style. It will also, as we will see, allow us to recover Johnson-Lindner-Strauss and as we'll see later in the chapter in compressed sensing, right, when we cover it maybe next week, then we'll see that will actually allow us to recover a lot of the theorems in sparse recovery using this. So I will not prove Gordon's theorem here, but before we go on, let me say a few words about the proof. Again, this is a very nice, I mean, it's available in the notes. It's actually a very nice homework problem to just try to work it out. At least this part. This one is a bit trickier. But the idea is to view this as an empirical process, right? What is an empirical process? Like a Gaussian process is something where we have, a bunch of random variables indexed by some set. The random variables are Gaussian, and we take the expectation of the max. Of course, you might notice this is not of that form, right? This random variable is not Gaussian, right? It's some absolute value of some Gaussian. But it's not hard to see, okay, let me see if I change this, right? That this is the same thing as maximizing now over some, say, vector V in the sphere now of dimension k minus 1, right? And now instead of taking the norm, I can just take the max with V transpose on this side, right? Because this will be exactly the norm of this vector, right? And now it's a Gaussian process indexed by this V and this X, okay? And now the idea will be to compare this Gaussian process, this comparison, Gaussian comparison inequalities like Slepian inequality, okay? And what they allow you to do, and Sudakov, Fernik, and so on, they're somewhat similar. What they allow you to do is to compare Gaussian processes with other Gaussian processes, right? By comparing how much covariance these Gaussian processes have, you can argue that one has a bigger maximum than the other in expectation. And the idea will be to compare to a linear one, right? Something like maximize of the same style of something like V transpose times some random vector, say U plus, right, another X transpose plus some other random vector, say G, right? And to come up with these in a clever way such that you can argue that the maximum here is bigger than the maximum there. And then when you analyze this process, right, because V is on the sphere, you get essentially a 1 on this side once you do it right, and you get the Gaussian width here, right? Normalized, of course, right here, you instead of a 1, you would get an AK. So after you normalize things because of the AK here, you'll get something like 1 plus the Gaussian width over AK, right? Where the 1 is coming from a term like this, and the AK from a term like that. Okay? Very similar to how one can prove that the spectral norm of a Wigner matrix in expectation is smaller or equal than 2, right, which is an excellent homework problem. This is essentially the same proof. The one here is a little trickier because you have to do Gaussian comparison with a max min, right, and or a min max, and then in order to do that, you have to compare with the Gaussian process that's similar to this, but it maximizes over one variable and minimizes over another. And when you do that, what you get is exactly this 1 minus instead of the 1 plus, and this is where these terms come from, right? So I highly recommend taking a look at the notes for the proof. It's the kind of proof that is sort of nicer to read than for me to write, because you have to come up with this construction of this Gaussian process and then compare. Okay, so what we saw is that, here if we have the map AKG, where G is a K by D matrix, that this sort of preserves the norm up to 1 plus or minus, right, WS over AK, right? Because it was the, right? So preserves norms up to this, right? But what we always saw was this theorem, Gordon's theorem in terms of expectation, right? But now, by now, we know how to transform this into tail bounds, right? We can simply use Gaussian concentration, right? In fact, right, it's not hard at all to see that the function f of g, right, being just exactly the function we're interested in. Let's say to take the max, right, the max over x in S, right, of 1 over AK g x, right, to see that this map is one Lipschitz. Or in fact, it's one Lipschitz even without the 1 over AK, right? So, right, that this map is one Lipschitz, right? So how do we see that something is one Lipschitz? We want to, right, take the absolute value of the difference between f of g1 and f of g2, right, and show that it's more equal than the L2 difference between g1 and g2. So we can take max x in S, g1 x, right, g2 x, right? And of course, this is smaller than if I just take, the max of the difference up here, right? It's the same thing. We've done this a few times. g1x minus g2x, right? Now triangular inequality, equal max s in S, right? g1 g2x, right? The L2 norm of this vector. But then, of course, now instead of optimizing over S, I can even optimize over the whole sphere, right? And it's just the same, the smaller equal, right? Because I'll be optimizing over something bigger than the spectral norm, which of course is smaller equal than the Frobenius norm, right? We've seen this proof a few times, right? So this is one Lipschitz. Okay. And one can also show the same way that that if I take, the minimum will also be one Lipschitz, and now we can use Gaussian concentration. Okay, so now if we use Gaussian concentration on this quantity we get, okay, so I'm going to erase this. Okay, so what do we get? We get, right, that the probability, right, that this quantity, right, the probability that this maximum, right, we have to do it without dividing by AK because that's the function is one Lipschitz, but of course there's no difference. Gx, it's bigger or equal than its expectation, right? So we have to multiply by AK on Gordon's theorem. We had 1 plus Gaussian width over AK. So now it's AK plus Gaussian width plus some T, right? That the probability that this is bigger than that is smaller or equal than, right, exponential of minus T squared over 2, right? And the exact same thing for the lower bound. Right, so of course now we could divide everything by AK, right, and getting 1 plus WS over AK plus T over AK, right? Even an AK would go over there. I mean, we'll do that in a second. Right, so min X in S, G X being smaller or equal than, right, now is AK minus WS minus T, right? The probability of this happening is also smaller or equal than exponential of minus T squared over 2. right? So now we get tail bounds for the deviations, right? So now we can use these to say that with very high probability, right? We just have to renormalize this. With very high probability, we have that that most norms are actually kept. Okay, so let me now write that statement. Right, so we just have to divide these by AK. Okay. Right, so we get a statement with bounds, right? This is a theorem in the notes, that if G, right, so this is a theorem, if G is a matrix that's K by D, right, with IID and 0, 1 entries, right? S in SD minus 1 closed, right, is a closed subset of the sphere, then, right, we're going to say that the norms are kept up to epsilon, right? So epsilon needs to be bigger than, right? The norms will be kept once I divide by AK up to roughly WS over AK. So if epsilon is bigger than WS over AK, then with probability, with very large probability, we'll see in a bit what it is, we have that yeah, that this will keep the norms up right, and if you wanted something about the norm squared, we just have to transform epsilon, you know, into, say, roughly 2 epsilon, 2 epsilon plus epsilon square, or 2 epsilon minus epsilon square, plus. Okay, and this will follow exactly from here, right? We just have to set epsilon. We divide by AK here, we get, right, if we divide by AK here, and here, and here, and here, right? I just have to set epsilon to be equal to WS over AK plus T over AK, right? And so that's why epsilon T needs to be positive. That's why epsilon needs to be bigger than that. And if you work out the probabilities, what you get is that this is with probability bigger or equal than 1 minus 2, right? Because we're going to need to union bound these two things, exponential of, right, exponential of minus k, right? The k will show up because it will be the ak squared, right, which is roughly k, epsilon minus ws over ak squared, right? It's what works out when we work out, right, what t is as a function of epsilon, you get exactly this, right? Then this will work for all x in S, right? And now we have a Johnson-Lindner-Strauss type statement, right? That, well, it's not really a projection, but almost a projection. So if you take a Gaussian matrix that goes from d dimensions to a lot less, to only k dimensions, then and with IID entries, then for a subset that's closed, and you pick S to be a closed subset, I mean, technical requirement, then basically you will keep with very, very high probability, where the probability of failure is exponentially small, you will keep the norms of the vectors up to epsilon, where epsilon is roughly the Gaussian width over AK, right? And remember that AK, right, AK was roughly square root K, right? It was smaller than square root K and bigger than square root K times a tiny thing, right? This root of K over K minus 1, right? So it is bigger, is smaller or equal than this, and bigger or equal than something that's essentially the same, right? Okay, and so this is a theorem that will be very, very useful. Okay, and so one thing that we can immediately see as well is from here is actually Johnson-Lindner-Strauss. I mean, not exactly, because this isn't a projection, but it's easy to see the implication of Johnson-Lindner-Strauss, or I should say an analogous result, right? Since this isn't a projection, this is not quite the same as Johnson-Strauss, but since this will be almost a projection, it almost is. But this can be viewed simply by noticing, right? Johnson-Strauss can be essentially viewed, or at least, you know, a completely analogous result can be obtained by just noticing that the Gaussian width of a set S is always smaller or equal up to constants than the log of the size of S, right? So this says that for a set S, you know, all you need is K to be, right? I mean, another way of seeing this, right, that AK should be bigger, right, as we said, than the Gaussian width, is just saying that K should be bigger than the Gaussian width squared, right? And so this immediately tells you that the amount of dimensions you should send to is always smaller or equal than log of the number of points, right? And why is it now? Why is this true? Okay, this is easy to see, right? Because the Gaussian width of a set S, right, is just the expected value of the max x in S, right, of GD transpose X, right? But for every 1 point, this is a Gaussian 0, 1, right? Because GD is a Gaussian, a standard vector, you know, standard d-dimensional Gaussian. X is a norm 1 vector, so their inner product will be a Gaussian, random variable, a one-dimensional standard Gaussian. And so this is just the maximum of right, it's just the maximum of size of S many Gaussian, standard Gaussians, right? So this is like, right, I can index this now with some, let's call this GX, maybe I should say GX, right? These GX is a random, just a random one-dimensional Gaussian, right? So this means that this is we're just taking the expected value of a maximum of size of S Gaussians. Let's say the size of S is N, right? We're just taking the maximum of N Gaussians. Regardless if they're independent or not, the maximum is always bounded by something like a square root of, by a constant times square root of log of how many of them, right? One easy way to see this is to do a union bound, right? If you look at the probability that the Gaussian is bigger than some t, will be something like e to the minus t squared, right, up to some constants and so on that I'm not worrying so much about for the sake of this discussion, right? But the probability that the Gaussian is bigger than some t will be something like e to the minus t squared, right? And so I need to union bound over n things, right? Because I want to make sure that none of the n Gaussians is bigger than that, because that's sort of what the maximum of the n Gaussians would be. And so, right, this means that I need a 1 over n to show up, right? So that I can union bound over n things. And so I need something like e to the minus t squared to look like 1 over n, right? And so I need the t squared to look something like log n. And so I need t to look something like square root log n, right? So if t is much bigger than square root log n, then this will be much, much smaller than 1 over n. And so no Gaussian, when I pick n Gaussians, no Gaussian will ever be bigger than square root log n, right? Times some constant. Okay, and so this immediately recovers Johnson-Strauss, and he tells us, well, up to the fact that this isn't actually a projection, but at least morally recovers Johnson-Strauss. And it tells us that if we know more about the set S, we can potentially do a lot better, right? If we know that the set S has some special structure, maybe we can get this bound much, much smaller. Or maybe we can even understand infinite sets S, right? Like the set of all natural images and so on and so forth. And this is in fact what we're going to do in the next lecture. But before we do that, I just want to show what is often known as Gordon escape through a mesh theorem, which is sort of a direct, I mean, almost direct application of this. I'm not showing the proof here, but it's something that's nice too, because that's the theorem that actually has a name. But, right, but as you see, it's not a, you know, it's definitely not a surprise after what we saw now. It's just a statement about how, right, you can ask for a weaker thing, which is instead of keeping the norms of all the vectors, I just want to not send any of my vectors to 0. I don't want any of the vectors in S to be in the null space of my map G. right? So in particular, if I keep its norm up to even a constant of 0.9, then for sure I don't send it to the null space, right? And Gordon escape through a mesh theorem is exactly about understanding the probability that you send it to the null space. Okay, so it's formulated usually as, because the null space of this Gaussian matrix is just a random subspace of dimension d minus k, the theorem is usually stated in terms of a random subspace. So Gordon escape through a mesh. Gordon's escape, right, is when the subspace escapes through a mesh, right? So just says that when I have a set S, okay, it can be in the sphere, but here, because it's about intersecting a kernel, right, doesn't even matter. The set S in D, say closed. Then take random and uniformly random, right, completely uniformly random, n minus D, sorry, D minus N, D minus K, right? It's the kernel D minus K subspace, right, uniformly over all subspaces over the Grassmannian manifold, right? This is like the kernel of the matrix G, right? Then we have that the probability, right, that this intersection is not zero is small, provided that you know, k is bigger than the Gaussian width squared, right? But the way we write this, the way this comes out once you work out the proof, okay, this is 7/2 expected value of some, right? There's some constants, and then here what you get is exactly what you would expect, right? AK minus WS squared, right? So it tells us that where AK, of course, is that quantity, the norm of the Gaussian vector, right? Which we know is smaller or equal than square root k, equal than. Okay, so this is usually how Gordon escape through a mesh theorem is stated, right? But if we take G to be a K by D matrix, and this to be simply its random, the kernel, right? The kernel is a random subspace of dimension D minus K, completely uniform. And it intersecting, if you keep its norm even up to 0.99 multiplicative factor, then if it wasn't zero before, it's not zero after, right? So your kernel is not intersecting the set S, and you get exactly this, right? But oftentimes, the theorem of Gordon escape through a mesh is stated this way, but this was, I believe, maybe the goal at the time when Gordon's theorem was developed and so on. Okay, so what we're going to see next is we're going to talk about measuring the Gaussian width for sort of less explicit sets, like the set of all sparse vectors, the set of all low rank matrices, and so on, and the implications that this will have for compressed sensing. Okay, thank you.